Hello, hello. I just wanted to give a quick summary of our new paper that's coming out now. This recording is predating the paper release by a few days. There's an embargo on the paper. It's published with Wiley academic publishers, and it's published in the journal Terra Nova, the New World. And it's a rapid communication. It's an invited paper by the editors. And let me share my screen now. It's, of course, about Iceland. And here we are. It's the paper here. And it's on the Fagradalsfjall and the Sundhnúkar fires, fires being an Icelandic expression for multiple eruptions in short sequence. That's what's called a fire. And it's about the rapid eruptions, rapid sequence of eruptions in the Reykjanes area. And here it's a team of authors, including Francis Degen at Uppsala, Tor Tordarsson from the University of Iceland, Ari Tryggvason from Geophysics here in Uppsala, Lucas from the Czech Academy of Sciences, Will from the University of Iceland, Björn Lund from Geophysics here in Uppsala, Ilya Bindeman from Oregon University, and Arman from the University of Iceland as well, and James Day from Scripps. So the story is that we're trying to answer one big question, and that is, are we dealing with a multitude of magma reservoirs? Are we dealing with a single magma reservoir? Is all of this magma from the last eruptions coming through a single system, or is it multiple deep fingers? And it goes back to the notion published by some Icelandic colleagues that we might have mantle-fed eruptions, i.e. fingers of material that come straight up from the mantle. If that is true, then of course, is each of these eruptions a separate finger or a separate pulse from the mantle, or are we dealing with a complicated plumbing system, a complicated magma supply system? So looking at this, there we have a map, and this is looking at data from the different Fagradalsfjall eruptions, Geldingadalur, Meradalia, and Litli-Rutur, but also the Sundhnúkar eruptions. And this has only data from the December Sundhnúkar. We now have samples from the January, February, March, etc. eruptions as well. They're in progress, but this was, of course, a geochemical approach and a geophysical approach, and it takes some time. So we have to now continue to work on the eruptions from 24, but this includes the Sundhnúkar eruptions from December 23. So this is a diagram that's been around in the literature for a while. It goes back to Sæmundsson, and this is showing these major eruption periods on the Reykjanes Peninsula. Let's see, we can probably go in a little more. And here we have these eruption periods interrupted by gaps, and there's these 800-900 year gaps, and then we have a new eruption episode that affects large areas over the peninsula. And now we have the Fagradalsfjall and now also the Sundhnúkar systems, the lineaments erupting again. So there is a good case to be made that maybe we're dealing with the start of a new eruption. The time would fit, and therefore we have the almost unique opportunity as scientists now to understand how these rhythmic pulses of large-scale volcanism on the Reykjanes actually work. So, and here we have some sketch diagram to put out the hypotheses. So we have some plume-related magmatism in central Iceland. It's feeding onto the Reykjanes. So here we have the mantle plume. It's probably coming from very deep inside the earth. And there we have these lineaments, these shear zones that are actually forming volcanic lineaments. And the hypotheses out there, as I said, I mean, there was an early paper saying it's all coming from the mantle, from a reservoir, and the mantle going straight up. And then is there one reservoir, or are these independent fingers? Then this diagram here shows that potentially we're talking about a multitude of smaller systems with somewhat larger reservoirs, maybe in the lower crust, and then smaller pockets in the upper crust. And then there's, of course, a case to be made that potentially we have a large underlying magma reservoir under the entire peninsula that's only starting to wake up now. If that's the case, we might have effectively multiple eruptions along the peninsula simultaneously. And to understand which of these models is the most likely, which of them applies, will actually help us prepare for future eruptive scenarios for the next years to decades potentially. So this is important here, and what we did is we did some geochemistry, and now I need to kind of zoom out a little. So here in yellow we have the Geldingadalë eruptions. Meradalë is the green, and the Litli-Ruta the blue data. The Meradalë and Litli-Ruta data is all new data. The Geldingadalë goes back to the Bindemann paper from 2022. And there is the Sundtnucker samples in red, the first Sundtnucker eruptives. And what we see here for MgO, there is a semi-continuous trend. And what we see here for chromium in parts per million as well. There's a few exceptional samples here, and that can be discussed. We consider them as outliers. But overall, the trend is pretty continuous for these elements. There we have potassium over titanium oxides. And again, apart from this outlier suite here, we have a pretty continuous trend. And this is true for various ratios. And ratios are, the important thing about ratios is they're a bit like, well, they don't change too much, even with fractionation processes, because they affect the different elements in a relative way. So the ratio often stays the same, even if you extract certain elements. But here we get an indication that these ratios are not changing, meaning this is actually a connection. This is a geochemical connection, a lineage as we call it, and therefore it implies that there is a relationship between these. If this was a completely different magma that comes up straight from the mantle from a different source, we would expect a different ratio to apply. So here, these continuations imply that the magma that comes out at Sundtnucker, or came out in December at Sundtnucker, is actually closely related to the magma that was erupting at the Fagradals eruption. So this is an important establishment, and it's an important fact to establish. And then we looked also at mineral chemistry. Here's a few microscope images, and there's of course a lot of olivine in there, but also plagioclase, tiny little bit of pyroxene, and also a little bit of oxide minerals. So but here what we see is in this scandium versus nickel diagram, which is laser data from olivine crystals, we see the different suites. And again, there is a seeming continuation. And we have microphenocrystals, tiny little crystals, and phenocrystals, larger olivine crystals, and they kind of overlap here. And there in this diagram, manganese versus zinc, we see that the larger crystals are from Sundtnucker. They overlap with the Fagradalsfjall data, while the microphenocrystals, the late-grown crystals in the matrix, they continue this trend towards higher manganese and higher zinc values. And that seems to be also an indication that we are looking at a suite from a parental magma to a more differentiated magma. So this means what we can say, at least for the December eruption, is there is a link between the Fagradalsfjall and the Sundtnucker lavas. They came from a similar suite of magmas at probably somewhere in the crust. And to find out where this happens in the crust, we employed some geophysics, and here we did some seismic tomography. So looking at all the earthquakes, it allows you to check how the P&S waves are moving. And I'm not a geophysicist, that's why I need my geophysics colleagues. And they can then look at where these earthquakes produce different wave patterns and different velocity changes, and that allows to say, oh, there's an anomaly in a certain area. And this is what we see here. We see an anomaly at about 10 kilometers depth, or about 9 to 12, with a heavy kind of color change or heavy velocity change of the seismic waves here in this area. And that allows to actually say that's the main reservoir. There is a resolution problem a little bit below there, so we're losing kind of information, but we likely have a major reservoir. There is no deeper major earthquakes recorded. All these dots are earthquakes here. Let's see, can we go further? All these dots here are earthquakes from different times during the eruption sequence. Here's the different years and the different months, and this implies that there is a main reservoir here and not necessarily a much deeper one. And it's also not along the entire peninsula. It's actually just beneath Fagradalsfjall, and it seems that the earthquake patterns define a pathway that goes, in this case, towards the west. So this main reservoir seems to feed both Fagradalsfjall and Sundnøkka. There is a smaller reservoir here, and you can see that clearly in the seismic patterns, but this is the one that bulges up and inflates, but it is likely fed from the central one. There's nothing underneath here in terms of earthquakes, and therefore this is the main culprit reservoir that causes the Fagradalsfjall as well as the Sundnøkka eruptions. And for all we can tell, this is still the case for the January, February, and as well as for the May and now June eruption. So although the latest eruption is calming down now, praise the Lord, but it might actually come back because it's swelling again. So the Svartsengi system here has again a swelling that started, so likely we will have more eruptions there. So that's the paper, and of course we acknowledge many colleagues here, and this is how you cite our paper. I'll put a link into the box below. It is actually open access, so anybody can download it. It's freely available. So, and this is an important finding. We're not talking about giant magma reservoir. We're also not talking about fingers that come up from the mantle. We are actually, let me bring you back to the hypotheses cartoons. We are actually not talking about this. We're not talking about this right now, at least. This is the most likely scenario we're dealing with. If there is sustained magma intrusions from the mantle into the crust for the next years and decades, it may come to this, but it likely has little resemblance of this model here, which some colleagues published early in the eruptive sequence after the Fagradals eruption started. So thank you very much, and I hope you found this interesting. Many people on YouTube asking me, what are you doing with the samples? What is the results? Can you show us a little more? And so I tried to make this video now. The release date is 26th of June, and I hope I will release this video before. The publisher has embargoed it, so I cannot actually share this before. So this is why this is a pre-recording, but on the release day, this video will come as well, and the link to the paper. And hopefully this will help our colleagues in Iceland to think about how to kind of work with the volcano around about Grindavik, and how to kind of prepare for the future evolving scenarios that we are likely to expect. So thanks, Emil, all the very best, and thanks for your support of the YouTube channel. It's very much appreciated. Okay, bye-bye, all the best.